This experiment focuses on the properties of gases and the ideal gas law. In chemistry, there are a lot of different reactions that can generate a gas compound or something in the gas state. Things like the reaction of an acid with metals will generate hydrogen gas. Also, in this specific experiment, you're focusing on the reaction between an acid and carbonate to form the gas of carbon dioxide. When an acid is mixed with a carbonate, the gas that's generated is carbon dioxide. And throughout this experiment, you're looking at these properties and seeing how the gas is formed, and then how you can measure that and relate that to the varying properties of temperature, pressure, and volume.
The ideal gas law is an equation that relates 4 different quantities that are measurable for a gas. The amount of gas that there is, or how many moles of the gas molecule there is, the volume or the space that it takes up, the temperature that the gas is in, and the pressure that the gas is under. There are 3 different forms of matter. There are solids, liquids, and gases. And different molecules and different compounds can exist in all 3 of these different states of matter. But gases in particular have some unique properties associated with them. Where solids are very compact and rigid, a gas molecule or gases are very expansive. The molecules inside the gas have a lot of energy, they're moving around a lot, and because of that, the temperature can affect how fast they're moving around and how much they're moving around, as well as the pressure, how many times the molecules bump into each other or bump into the sides of the container. And these 2 properties, as well as the amount of gas or the number of moles that would be present in a container, can affect all of the other properties. And the ideal gas law is a way where you can relate these 4 properties together, and you can see if you change one of them, how that would affect the other 3. The ideal gas law is actually a combination of at least 3 different proportionalities, or 3 different laws all rolled into one. The first law would be Avogadro'S law, and this relates the amount of moles of a gas, or the amount of molecules, and the volume. It typically makes sense that if you have more of something, it's going to take up more space. And that is the entire law of Avogadro's law. The more you have, the more space it will take up. These 2 components are linearly related, and they're directly proportional. Again, if you have more of something, the volume will increase. If you have less of something, it will take up less volume.
Avogadro's law is the relationship between amount and volume. That is the number of moles of a gas and a volume. It stands to reason that if you have more material, the volume or the space it takes up will be increased. There is only so much air in this balloon at the moment, but by adding more amount, by adding more moles, the volume increases. These 2 properties are directly related, and as one increases, with all other properties being the same, the other would also increase.
The next component of the ideal gas law would be Boyle's law. And this is a relationship that combines pressure and volume. If you have a set number of moles or a set number of molecules of gas inside a balloon and you squeeze it, you're lowering the volume, but the pressure inside is increasing. These two components have an inverse relationship. As provided everything else is staying the same, if the pressure was to increase, that would be the result of the volume being decreased. If the volume was to be increased, the pressure inside would decrease or lower. And this is because when the gas molecules are moving around, they're bumping into each other, they're bumping into the sides of the container. That's what generates, or that's what pressure is. It's those gas molecules bumping into each other and bumping into the sides of the container. If that same amount of gas is now spread out over a larger volume, they're not going to be bumping into each other as much. They're not going to be bumping into the sides of the container as much because there's more overall space for them to move around. And that means the pressure inside would be decreased because there is less of that bumping into each other.
Boyle's law relates volume and pressure together. In this setup, initially there's a volume of 65 milliliters of gas. The pressure is 1 times 10 to the 5th pascals. As the volume is decreased, you can see the pressure increase. At a final volume of 30 milliliters, the pressure reading itself is a little over 2 times 10 to the 5th pascals. The same can be true by increasing the volume. If the starting volume is at 30 milliliters and the overall volume is increased, the resulting pressure is decreased. These two properties are inversely related. As volume increases, the pressure decreases. As volume decreases, the pressure increases.
The last portion of the gas law would be Charles's law. And this is a relationship that combines temperature and volume of a gas. So we already saw that molecules will move around in a container and bump around into each other, and that will increase pressure. But what if you want pressure to be held constant? So in the case of atmospheric pressure, the air, that is a constant pressure, but the volume of gas contained in some amount of air can be different depending on the temperature. As you increase temperature, the molecules have more energy. They're moving around in that space more and more. And if pressure is always the same, but the molecules are moving around a lot more and moving around a lot faster, they're not going to bump into each other, but now they're going to move in more area. They're going to spread out more. And that's why in Charles's law, the relationship is that if temperature increases, with everything else being the same, the volume would also increase. These two are linearly related and directly proportional. If you were to decrease the temperature, the amount of space that those gas molecules take up would be lowered.
Charles's law relates the two properties of volume and temperature of a gas. These two properties are directly related to one another. As the temperature of an amount of gas increases, the volume or the space it takes up will increase. The same is true if you lower the temperature. The volume or space that the gas takes up is decreased. This can be even seen at home with a balloon. By blowing up a balloon, you can see the total or the starting volume of it. If this balloon was placed in a freezer, the overall volume would decrease, and you could visually see that.
By taking all three of these relationships, Avogadro's law, Boyle's law, and Charles's law, and combining them, you end up with this equation, which is the ideal gas law. PV equals nRT, where P is the pressure of the gas, V is the volume of the gas, N is the moles of gas or the amount of gas molecules, T is the temperature, and R is the gas constant. So when you're using the ideal gas law, this is one of the equations where you generally are asked to memorize. And when you're using this equation, the temperature should be in units of Kelvin. And to convert between Celsius and Kelvin, it's the addition of 273. At 0 degrees Celsius, the temperature in Kelvin is 273. The basis for the Kelvin temperature is absolute zero. The lowest possible temperature in physics would be 0 Kelvin, and everything goes up from there. And it's scaled based on Celsius, at it with 273. The gas constant is a unique property or a unique constant for these different gas molecules. But something about the gas constant that you do need to pay attention to is the units that it's in. Both pressure and volume can have a number of different units. You could measure the volume of a gas in liters. You could measure the volume of the gas in milliliters, cubic meters, cubic feet. So there are different units you can measure volume in. Likewise, there are different units that you can measure pressure in. Pressure can be measured in pascals, bars, atmosphere, torr, millimeters of mercury, PSI. There are a lot of different ways that pressure can be measured, a lot of different types of units. And instead of interconverting all of these things, many times the value of R is just changed depending on what units you happen to be using. These four values listed here are the most common, where typically it's in the unit of meters cubed pascals over moles per Kelvin, or liters atmosphere per moles Kelvin, or liters bar per mole Kelvin, or liters torr over moles Kelvin. And the pressure unit of torr is the pressure unit of millimeters of mercury. If you've ever heard pressure being discussed in units of millimeters of mercury, this is the same unit. Torr and millimeters of mercury are the same thing. If you go further in chemistry and physics, you'll also be looking into thermodynamics, which also uses the gas constant in a different context, looking at the energy unit of joules. And so as you're going through the experiment, you're looking at the different properties of gases and how it relates to moles, volume, temperature and pressure, you're going to be utilizing this gas constant in the ideal gas law, which is PV equals nRT, and you can go through and calculate and determine how these different properties are interrelated to each other. The ideal gas law is going to be a home experiment, or an experiment that you can do at home by yourselves. And really what you'll need is baking soda, vinegar, and it can be any variety of vinegar, either white vinegar, apple cider vinegar, red wine vinegar. Any vinegar should be able to work. You'll also need a little bit of dish soap, a ruler or some sort of measuring device, teaspoon and tablespoon, just to measure the volumes or measure the amount of water and baking soda and vinegar as you're mixing these things together.
The experiment itself looks at the reaction between a carbonate compound and acetic acid or vinegar. So in this reaction, you're mixing baking soda or sodium bicarbonate with acetic acid or vinegar. The overall reaction from this produces water and carbon dioxide gas. It's this carbon dioxide gas that you're going to be measuring the volume of when it reacts. Initially, it's a little difficult to measure the actual volume of carbon dioxide that's generated. But through this experiment and the use of dish soap, you're going to be measuring the actual volume of carbon dioxide gas that's present, and then comparing that to the calculated volume that you would determine based on the ideal gas law.
The chemical reaction that's occurring in this home experiment is the reaction of baking soda or sodium bicarbonate and vinegar, which is a dilute form of acetic acid. So CH3COOH, or acetic acid. And when these two components react with each other, they form the sodium acetate salt, and this would just be an aqueous salt in solution, and one molecule of water and one molecule of carbon dioxide. Because both the sodium bicarbonate and the acetic acid are solutions already in the experiment, you're looking at the specific reaction or the net ionic reaction of just the bicarbonate ion and the H+ ion, or the acid ion. And this is the reaction that's happening. The acetate ion that's floating around, as well as the sodium ion, do not take part in the reaction. They're spectator ions. They're both aqueous on this side in the reactants and in the products. So the main reaction is just the net ionic reaction is the bicarbonate ion reacting with H+ to form carbon dioxide gas and water. And this reaction is all one-to-one. For every one bicarbonate ion that is a reactant, you are generating one carbon dioxide and one water. But because carbon dioxide is generated, you're looking to see this gas. You're measuring how much carbon dioxide is generated looking at this. So while we're before in previous experiments, you're looking at observations and moles, or the mass of carbon dioxide. This one is specifically looking at and measuring the volume of carbon dioxide. So because this is a home experiment and it's dealing with the ideal gas law, looking at pressure and volume and temperature, you need to be able to figure out or find those environmental properties. So wherever you happen to be when you're performing this experiment at home, you need to know what is the pressure and what is the temperature where you're performing this reaction. So the temperature can generally be found on any home thermostat. There are apps, and you can just see what is the temperature in your kitchen where you're performing this experiment, or wherever you happen to be performing it. Many times in the US, the temperature is given in units of Fahrenheit, and you would use this equation here to convert Fahrenheit to Celsius. And the ideal gas law, again, needs to be in units of Kelvin. So you would take that Celsius temperature and add 273, and that would give you the temperature in Kelvin that you would use in the ideal gas law. The pressure reading will be whatever your current barometric pressure is. And this can be found on a lot of different weather websites. So things like weather.gov or weather.com, or there are a lot of different weather websites that can give you the pressure reading. What is the barometric pressure? This particular website, weather.gov, it's given in units of inches of mercury, but it's also given in units as MB or millibar. And 1 bar would be equal to 1,000 millibar. So when you're going through and doing this, you'll have units of liters and bar for the pressure, so that way when you go through and look at that, be sure to choose the correct R value or the correct gas constant when you're calculating in the ideal gas law. So in preparation for the experiment, you do need to do a few initial calculations. You're preparing a solution of baking soda or sodium bicarbonate. And while many times this may be listed on the packaging of sodium bicarbonate or of your baking soda, if it's not, 1 completely level teaspoon should weigh 4.8, exactly 4.8 grams. Other things to know, 1 tablespoon is equal to 3 teaspoons. So if you don't happen to have a tablespoon, but you have one of those disposable plastic spoons, that disposable plastic spoon is 1 teaspoon. And you could just use teaspoons throughout the entire experiment. And when it asks for a tablespoon, you would just use 3 teaspoons. But this is a chemistry class, and typically in chemistry, units are not done in volumes of teaspoons. So you will need to convert the volumes into milliliters and liters. And 1 teaspoon is equal to 4.929 milliliters. So the steps that you're doing is you're taking 1 teaspoon, you're dissolving it in 7 tablespoons of water. That will take a couple of minutes. And if you know the mass of baking soda, again, you're using 1 teaspoon, so you know the mass of baking soda, you can convert that into moles of baking soda or sodium bicarbonate using the molecular weight. And if you have a volume, a total volume in solution of 7 tablespoons, you can convert that into liters. So you would then be able to determine the molarity or the concentration of your baking soda solution. You'll have moles and you'll have liters. It also asks you to calculate the molarity of the vinegar solution itself. So vinegar is typically 5% acid, and most vinegars are labeled 5% acidity. And this means that if it's 1%, that means there is 0.01 grams per milliliter. So a 1% solution of acetic acid would contain 0.01 grams of acetic acid in every 1 milliliter. In the case of 5%, as most vinegars, this would be 0.05 grams in every 1 milliliter. And this percentage is a concentration, same as molarity. You have a mass, which you can convert to moles using the molecular weight of acetic acid, and you have a volume, which should be converted to liters. And from that, you can determine the volume of, the molarity of the vinegar. So starting out, you have your solutions prepped, you have the concentration and the molarity of vinegar, you have the molarity of baking soda, and then you can go through and perform the actual chemical reaction.
In the at-home experiment, the first step in the procedure is to prepare the baking soda solution. You will use exactly 1 teaspoon of baking soda, being sure that the teaspoon is leveled off. You want exactly 1 teaspoon of baking soda, the mass of which can be found on the packaging, but is generally believed to be 4.8 grams. After the baking soda is measured, you will be adding 7 tablespoons of tap water. When the water is added, the solution itself is mixed. This will take a few minutes for all of the baking soda to dissolve. Afterwards, you will have a solution of sodium bicarbonate. Based on the mass of baking soda that's used and the overall volume of solution, you can determine the molarity of your baking soda solution. With the baking soda solution prepared, you can measure out 1 tablespoon of your solution and place that in a glass or container, preferably one with straight sides. To the container, you will also add a small amount of liquid dish soap and stir the contents together. Based on the molarity of your baking soda solution and the volume of solution that you had used, you can determine how many moles of baking soda are present in your reaction container. Your baking soda solution is then reacted with vinegar. Vinegar is typically 5% acetic acid and is labeled as such on the bottle. 5% acetic acid means that for every 100 grams of vinegar, 5 grams is pure acetic acid. Using the volume and the density of water at your particular temperature, you can determine the mass of vinegar, and from that, the total mass of acetic acid. With the mass of acetic acid and the overall volume, you can then determine the molarity of vinegar and how many moles of vinegar are reacting. When you react your baking soda solution with 1 tablespoon of vinegar, the result is the gas formation of carbon dioxide. To measure the volume of carbon dioxide gas, you will be using geometry based on the diameter of your container, as well as the height of the bubbles. You can effectively calculate the volume of carbon dioxide collected. Using the moles of baking soda in each trial, as well as the temperature based on your thermostat, and the atmospheric pressure based on a weather website, you can calculate the true volume based on the ideal gas law. You can then compare these two volumes and determine a percent error. Overall, you will perform this reaction 3 times and determine the volume of carbon dioxide collected for each trial. Taking the average of these trials, you can compare that to the calculated volume based on the ideal gas law.
In this experiment, you're looking at the volume in 2 ways. You're calculating the theoretical volume using the ideal gas law, and then you're physically measuring the volume of the carbon dioxide in the reaction. So again, in the ideal gas law, you have the pressure, which will be the barometric pressure taken from the weather website. The volume of the gas, this is what you're solving for in the ideal gas law to calculate what the theoretical volume should be. You have the moles of sodium bicarbonate, so that was just calculated previously when you have the molarity of sodium bicarbonate, and you're measuring out 1 tablespoon, so you have a volume. You can calculate how many moles of sodium bicarbonate that was. And since the reaction for every 1 mole of sodium bicarbonate generates 1 mole of carbon dioxide, these 2 moles are the same amounts. So you don't need to convert anything. R is the gas constant. So again, make sure to use the appropriate R value depending on what units of pressure your weather website found. And then the temperature taken from your thermostat or thermometer or anything, and converting that into units of Kelvin. So that will give you the theoretical volume that the reaction should generate. However, in the reaction, you're measuring how much volume is actually created. And when you perform the experiment, the carbon dioxide gas that's generated in the reaction is being trapped in the soap bubbles. And what you can do is measure the diameter or the width of the glass or reaction vessel that you're performing the reaction in, and then how tall are those bubbles? What is the height that those bubbles reach using a ruler? And most times this would be best performed if you're using a glass that has straight sides or straight edges, so not something that's tapered. So that way it would be a perfect cylinder. And the volume of a cylinder is the area of the circle, so that top circular area, which is pi r squared, times the height of those bubbles. And that will give you the measured volume of carbon dioxide gas. How much gas was generated and then captured in those soap bubbles. And last, because now you have the theoretical volume, which was calculated using the ideal gas law, and you have the measured volume, which you measured using geometry, you can calculate a percent error. How far off is your number based on the theoretical volume of what the number should be? So you're going through, you're performing this reaction, you're performing it in 2 separate trials. You're calculating what the theoretical volume of gas generated should be based on the ideal gas law, and then measuring the volume of carbon dioxide that's trapped in the soap bubbles and determining a percent error for each one of those trials.
Overall, in this home experiment, you're combining a few different chemistry concepts. You're preparing solutions and determining moles of compounds. You're performing a reaction and looking at the observations that happen when a gas is formed. And then you're measuring the volume of the gas that's formed and using chemistry determining the percent error based on the ideal gas law. Hopefully, as you're going through and performing this at-home experiment, you get a good understanding of the properties of gases.